Today we're going to be doing a little bit of a calculus. We're going to use the equation velocity at time t is equal to 2t cubed minus 3t plus 2. Let's take a second and look at a graph of this equation. Here I have my v at t graph displayed. So I have v at t equals 2t cubed minus 3t squared plus 2. If I wanted to know the acceleration is the slope of a velocity graph. So I would take the slope over some amount of time. With calculus, though, we can do a derivative. That will take the slope at all points on this graph. Let's step back over to the board and take the derivative of this graph. Having looked at the graph, we know that acceleration is the slope of the equation. And in calculus, we know that as we get closer and closer in our delta t, it becomes a dt. So we have dv dt, the derivative of velocity with respect to time. Most of the time in AP Physics, you'll be able to use the power rule. To do a quick review from that in calculus, we take the exponent and multiply it by the coefficient, and then decrease the exponent by 1. So here's my first term. I have the exponent multiplied by the coefficient, and then the coefficient minus 1. And I do that with each term. So let's look at this one. If I don't have an exponent, I can assume that it's 1. So the second term, I have 1 times 3 times t to the 1 minus 1. And now let's look at the last term. There's no t here, so this is t to the 0 power. I'm going to write that in parentheses so we recognize that it isn't typically shown. So my exponent is 0, so I multiply that by my coefficient. And I'm not going to decrease the exponent here because the t isn't actually there. Now that I've written this out, I can simplify a little bit. 3 times 2 will be 6, and 3 minus 1 is 2. Minus 1 times 3 is 3. 1 minus 1 is 0. Anything to the 0 power is equal to 1. So t to the 0 is a 1. So I don't even have to write the t. It becomes a 1. So this is minus 3. The derivative of this equation with respect to time is 6t squared minus 3. Let's take a second and look at the graph of that equation. We've taken the derivative, we got 6t squared minus 3. You'll see that the slope is positive here, the slope becomes negative, slope is 0 in these two places. Let's compare this to the original graph. So I have a segment where the slope is negative and 2 segments where the slope is positive, and 2 places where the slope is 0. Comparing to the original graph, the slope is positive all the way through here. The slope becomes 0 at the peak of this. I now have a negative slope, becomes 0 again, and then positive the rest of the way. So this matches up. We did our derivative correctly. To figure out position, I need the area under the curve. So I need to figure out how much area is underneath this graph to figure out the position. We do that by taking an antiderivative, or an integral. Let's step back over to the board and see what that will look like. We recognize that from a velocity graph, position is the area under the curve of the velocity graph, which leads us to do an integral. I have my integral set up. I'm taking the integral of velocity and the integral of the equation with respect to time. To do an integral, I have to do an antiderivative. Remember the power rule for derivatives, I took the exponent, multiplied it by the coefficient, and decreased the exponent by 1. To do an antiderivative, I increase the exponent by 1 and divide the term by the new exponent. So it will look like this. In the first term, I've increased the exponent by 1 and then divided by that new exponent. Looking at the second term, my exponent is 1. I increase it to 2 and then divide that whole term by 2. In the last term, my exponent is 0, t to the 0 power. I increase that exponent by 1, so it'll be t to the first, and divide it by 1. However, all this does is tell me the shape of it. It doesn't tell me how far up or down it is. Since there's no limits on my integral, I have to add a plus c. So there is some value here that shifts the equation up or down. We have no way of knowing how far up or down this equation is. We just know its general shape. Let's simplify some of our terms, and then we will look at what this plus c does on a graph. I've taken the antiderivative. I got 1/2 t to the 4th minus 3/2 t squared plus 2t plus c. So this is the graph of that equation. The plus c, all it does is move the graph up and down. Desmos actually has a slider where you can adjust your plus c and you can see what it does to the graph. So you can see the graph is just going up and down. It's not changing the shape, not changing slopes. It's just moving where the graph is up and down. So plus c does nothing to the shape. All it does is shift it vertically. Let's go back to the board and take a definite integral. Let's try and figure out the position change over a certain time period. Now that we've looked at what the plus c at the end of an antiderivative does, let's do one that's a little more specific. Let's say I wanted to know how much the position changed from t equals 0 to t equals 2. So I know position is an integral of velocity, so I set up an integral. And because I know a particular time frame that I'm interested in, that puts limits on my integral. I'm interested from time equals 0 to time equals 2. So I use my lower limit and my upper limit. Now I can do the integral. We know what this one will come out to be, so I'll just skip to the final form of it. I'm going to include the plus c here. It won't change our answer, and we'll see why. A lot of times you won't see the plus c if we're doing a definite integral. You'll see why it typically gets dropped here in just a second. So I have my antiderivative, and I'm going to evaluate it. So you'll see a vertical line from 0 to 2. What that means, I take this 2, plug it into this equation, and then I take that, solve it, and subtract 0 plugged into this equation. So let's see what that looks like. In this first expression, I have 2 plugged in for each of the t's. In the second expression, I have 0 plugged in for each of the t's. Let's simplify and evaluate. Let's start with this first term. I'm going to do the arithmetic for it, and then simplify this as much as I can. I have 2 to the 4th, which is 16, times 1/2 gives me 8, minus 2 to the 2nd is 4. 4 times 3 is 12, divided by 2 is 6, plus 2 times 2 is 4, plus c. I'm going to simplify the second term a little bit. 0 to the 4th is 0, times 1/2 is 0. 0 squared is 0, times 3/2 is 0. 2 times 0 is 0. And my plus c's trail along. Everything in this goes away except the plus c. And I'm subtracting it, so let's simplify a little bit more. I have 8 minus 6 plus 4. 8 minus 6 is 2, plus 4 is 6. Plus c minus, all that's left over here is c. So I have plus c minus c, those cancel out. Anytime I'm doing a definite integral, those c's will cancel out, so you generally don't even see them included. So my position changed 6 units during those 2 time intervals.